Welcome back. In this section, we'll be looking at substitution methods for integration, which is a very important set of methods for us to find indefinite and definite integrals. So for this, we're doing sort of the equivalent of the chain rule, but for integration. We start off, we've got some sort of a function, f of x, little f of x, and we have an antiderivative for that function, and that'll be capital F. So when we are using integration by substitution, it's going to be for a case where we've got some sort of a product going on, where part of our product involves a function g of x, and the other part of our product involves the derivative of g of x. So when we're looking at things, it's going to be something where we see a function and we see that function's derivative together. So this is the idea that we're looking on that sort of lookout for some function of g of x combined with the derivative of g of x. So what we're going to do is a little clever substitution, and that will simplify our integral that we have here and make it easier for us to work with. So the idea is we start off saying, well, I want to replace g of x with some new function v. And of course, this v is going to also be a function of x. So v of x is going to be g of x. So if we're looking at what is the differential, so we know for if v is g of x, then the differential of v is g prime times dx. So that means that you've got a lot of things that can be substituted into your integral now. You could say, well, instead of f of g of x, g is the same thing as v, so you now have f of v. And g prime of x dx, that's the same thing as the differential dv. So g prime of x, we can replace that with dv. And what's that done for us? Well, it's basically replaced it. Instead of having a function inside of a function, we just have a more simplified function of v. And of course, we said at the beginning, we already know that this f has an antiderivative. Capital F is an antiderivative of that. So what we're looking for is an antiderivative of f with respect to v. Easy enough to do. That will be just capital F of v. And of course, plus your constant c. And then you can go backwards and say, now that you found your indefinite integral, you can reverse and say, well, v is the same thing as g of x, so this is capital F of g of x. This is one of those methods where, like a lot of things, it's easier to sort of pick up on what to do as you see some actions in process. So let's do a couple of examples and we'll sort of get the hang as we're going along with it. So for the first one, I'm looking at this, and the thing that's making me think about substitution, remember what we need to look for is, can we find something where that function's derivative is present? So if I'm looking at this, I'm looking for things and their derivative, and I can see, well, x cubed, its derivative is 3x squared, so I do have something and its derivative present. And in fact, I could go even wilder and say, everything inside that square root, the x cubed plus 1, its derivative is 3x squared. So I've noticed there's something whose derivative is present, and so now I'm going to start making my substitution on the side. I'm going to say, I'm going to let u be my x cubed plus 1, and now we're going to do our differential. The differential of u should be the derivative of this. The derivative of x cubed is 3x squared times dx. So now we're good to go because we're told that we have 3x squared dx being the same thing as du. So I can replace 3x squared dx. I also have something to replace the x cubed plus 1, so I can replace that as well. So let's do our replacing and see how this has simplified our indefinite integral for us. We'll now have, instead of 3x squared dx, it'll be du. And instead of 2 square root of x cubed plus 1, it'll be 2 square root of u. So it's a much simpler function now. Instead of integrating this messier thing with respect to x, we just have 1 over 2u to integrate with respect to u. or if I wanted to rephrase that, 1/2 u to the negative half with respect to u. And that's easy enough to do. I'll just use my power rule. So I'll add 1 to the power, divide by the power, and add my constant c. The half and the half, nicely enough, they cancel each other out. So I'm just left with u to the half plus c. And of course, we started off with an indefinite integral in terms of x, so we'd like our antiderivative to be in terms of x. So that's where we'll now go backwards and say, well, u was the same thing as x cubed plus 1, so we've got x cubed plus 1 to the half plus c. And there we go, that's my indefinite integral. Let's do another one. Again, always asking ourselves the question, do we see something where its derivative is present? So I'm looking at this and I can see if I'm looking at 2x squared minus 1, I know the derivative of 2x squared minus 1 is 4x. So I'm thinking for my substitution, that's what I'll do. I'm going to let u be 2x squared minus 1. And then for differentials, du is the derivative of that times dx. And the derivative of 2x squared minus 1 is just 4x. So that means for my integral, 2x squared minus 1 to the 20 becomes u to the 20. And 4x dx becomes du. And so it's a much simpler integral. One thing that I just have to caution here, and this is an important thing for any time we're doing substitution, if we're substituting, we have to be able to replace all of the x's with whatever the new variable is. So if I still had some x's floating around or dx's, then I haven't completed my substitution. So if you are doing a substitution and you have some leftover things, then you didn't do your substitution. Here I know that I'm on the right place because I started off with everything in terms of x and now everything is in terms of u. So finding an antiderivative, I can go ahead and do that. And then I can finally rephrase things in terms of x. U is 2x squared minus 1, so we have 2x squared minus 1 to the 21 over 21 plus our constant c. Okay, so here's where we get a slight twist in things. So up till now I've been saying we're looking for a function where we can find its derivative. And we don't have to find the exact derivative there. It can be off by a constant multiple, and that's still okay. So for example, I'm looking at that x cubed plus 5, and I can say to myself for that, its derivative would be 3x squared, and I don't have 3x squared here. I've just got x squared, but that's not a problem because this is just a constant multiple of x squared. So that's still close enough for me. And I'll show you how we'll be able to account for that, the fact that we have that missing constant. So first, if I start off, I'll say let's let v be this x cubed plus 5. And then for differentials, dv is the derivative times dx. And the derivative of x is 3x squared. So you notice we don't have 3x squared to substitute. We have x squared dx. And so, of course, that equation, that differential equation that I've got there, I can rephrase it and say, well, 1/3 dv is x squared dx. So now when I'm doing my substitution, the square root of x cubed plus 5, that's the square root of v. And then the x squared times dx, that's the same thing as 1/3 times dv. So I could write 1/3 times dv, or of course the 1/3, I could just in advance take that outside of my integral because I know that constant multiples can always be brought outside. So there we go. That's how I'm going to tackle that. I'll say it's 1/3 integral of square root of v. And of course, if I wanted to make things a little bit easier on myself, I'd rephrase that as square root of v as v to the 1/2. so that I get 1/3 v to the, adding 1 to the power, dividing by the power, plus our constant. And then I just need to clean things up, and then life is good after that. So I've got, when I, 2/3 should have been 3/2. When I clean up the numbers, 1/3 divided by 3/2, that gives me 2/9. And replacing v with what v is equal to, which is x cubed plus 5. And there we go. One thing, of course, that I haven't mentioned in a few videos, but I think is worth refreshing ourselves on, and I said this in the beginning of chapter 4.1, good to remind ourselves here too in substitution. If we're ever concerned that we're not right, we're wondering, is this answer correct or not? We can always check to see if it's correct by differentiating. That was the whole point of the fundamental theorem of calculus. It is that our derivatives and our antiderivatives are opposites of each other. So if I differentiate this function, 2/9 x cubed plus 5 to the 3/2 plus c, I should get my original function back. So if I did my integration correctly, then that's what I should have. And that's a way that we can check our work, which is kind of nice. This problem, we've actually did this one before. We did this back in 4.1, and if you're remembering from 4.1, we looked at this and said we didn't have anything to deal with products or anything like that, so we had no choice but to actually expand. Now we don't have to worry about expanding because I'm looking at this and I can see that even though it doesn't look like a product, it kind of technically is, because if I were to say that u is everything inside that cube, so in other words, if u was 3x plus 1, then as far as differentials go, du would be the derivative times dx. And I almost have that. I mean, I have just dx, but that's easy enough. If du is 3 dx, then 1/3 du is dx. So actually, I'm able to do a substitution, even though it doesn't look like there's two things. But technically there are. There is that cubing thing, and then there's the times dx. And I know that the 3x plus 1 cubed could now be written as u cubed. And dx is the same thing as 1/3 du. And again, you could either keep the constant inside or take the constant outside, whichever you prefer. When I take find the indefinite integral of this, I'll say, well, for u cubed, I'll add 1 to the power and divide by the power. So on the denominator, I'd have 3 times 4, which is 12. And so I've got 3x plus 1 to the 4 all over 12 plus our constant c. And that was, if you compare the answer that we have here to the answer that we found back in chapter 4.1, you'll notice how much faster this one was. So that's kind of pointing to how powerful is substitution as a tool. So I'm going to do one more here, and let's take a look at this one. Again, I'm looking at this, and if it was just secant theta tangent theta, that would be easy enough to do because I know what that is. Its antiderivative is secant. So I'm looking at that and saying, well, I can actually fix that, because if I were to let u be 4 theta, then du is 4 d theta, or in other words, 1/4 du is d theta. So this could be rephrased as integral of secant u tan u, and d theta is 1/4 du. And there we go. Now I'm easy enough to work from here on out, because I know antiderivative of secant u tangent u would be secant. And I can now go backwards and say, well, u was 4 theta. So I have 1/4 secant 4 theta plus our constant c.